Okay, time for today's lectures. Again, I want to thank each and every one of you for being here, for being a part of this class, okay, and for showing up on time. Okay, the focus of today's lectures will be on spring mass damper systems. In particular, we will investigate, we will study the impacts of the location of poles. And in the first part of today's lecture, we'll first study the zero input response of a spring mass damper system. Let's review what we have learned about the fabulous spring mass damper system. Okay, this is a schematic diagram of a spring mass damper system, and this is its equation of motion. M represents the mass, C is the damping coefficient, and K is the spring constant. Here, we have initial displacement y0, and we have initial velocity v0, all right? So this essentially is a 1 degree of freedom system. And typically, a single degree freedom system, especially mechanical system, can be represented as a second order differential equations. Now, to simplify our analysis, the first thing we want to do is we want to take Laplace transforms. Here, we'll keep the initial conditions. ICs here stand for initial conditions, not integrated circuit, all right? Now, so you can see initial displacement here. Here, you can see initial velocity here. After taking the Laplace transform of the entire differential equation, this is what we will get, which is apparently an algebraic equation. That is exactly the reason why we want to use Laplace transform in the first place. It simplifies our mathematical solution, because dealing with algebraic equations, as we said it again and again, it's usually much easier than dealing with differential equations. Now, we can rearrange this algebraic equation. And the purpose here is, of course, solve for y, because we want to know how the system responds to a given input, which is x in this particular case. Now, after dividing both sides of this equality by this polynomial, which is called, I'm sure you are very familiar with this term, which is called characteristic equation. This is what we will get. Apparently, this part is related to input, and this part is related to initial conditions. Therefore, by definition, this part of y is called the zero state response of the spring mass damper system. And similarly, this part of the response of y is referred to as zero input response. The focus now is, for the time being, is on this part, zero input response, okay? Now, since we are dealing with the second order systems, okay, as you can see, at the first glance, you see that for a spring mass damper system, it actually has 3 parameters, M, C, and Y. But what happened is that if you dig deeper, you will find that for a second order system, there are essentially only 2 key parameters, which we saw before. One of them is natural frequency, and the other is damping ratio, right? Now, natural frequency, we saw it before, is defined as the square root of K over M. and damping ratio is defined as by this equality. Remember that this is damping ratio. This is damping coefficient, all right? Essentially, they represent, both of them represent the damping effect of the system. The difference is that you can see eta, which is the damping ratio, as a normalized damping coefficients. Normalized to what? Normalized to the mass. Normalized to omega n, which is the natural frequency. All right? Now, if we introduce these two parameters, and we saw it before, we know that this so-called transfer function can be rewritten as this. All right? So after introducing omega n and eta, we see that for transfer function, actually what we have are two key parameters. One is eta, one is omega n, because once eta and omega n are known, the locations of the poles are specified. All right? If you know omega n, you know eta. You know natural frequency, you know damping ratio. You know where the poles are. Okay? And that pretty much determines a very big proportion of the dynamic characteristic or behavior of a spring mass damper system. That is the very reason why we say natural frequency and damping ratio are the two key parameters for spring mass damper system, or generally speaking, for linear time invariant second order systems. Now, how do we deal with this problem? Okay, how do we solve such an equation for zero impulse response? Let's first go back to what we have learned in the course of engineering mathematics. In that course, we were taught to deal with such an homogeneous linear ordinary differential equations with constant coefficients. Constant coefficients here represent such a dynamic system is time invariant, right? Okay. Now, homogeneous means we don't have any input, which means what we are going to solve, what we are going to determine is the zero input response of the system. All right. So in the course of engineering mathematics, how do we find y? How do we solve this equation to determine what y should be? Please remember the first step of the solution procedure is always this particular assumption. We assume the zero input response or the homogeneous solution for this ordinary differential equation can be represented as e to lambda x. E apparently is the exponential function. Lambda is what we call, in the course of engineering mathematics, is what we call eigenvalues, right? Or sometimes we refer lambda as characteristic values, okay? But in the domain of control, lambda is often called the pole of the system, okay? Now, in different domains, we use different terminology, but eventually they represent the same thing, all right? Now, to determine the eigenvalue, what we need to do is we substitute such a representation into this differential equation. Therefore, we need to know what y dot is. We need to know what y double dot is, okay? And we plug them all into these differential equations. And it has been shown before in this class that these differential equations will be converted into this algebra equation. Now, to this equality to be true, it can be shown that this polynomial has to be true, because if this is true, what we have is y equal to 0. It is a solution, but it is a useless solution, That is the reason why we call such a solution trivial solution, right? All right, so we need to determine the root for this second order polynomial, okay? Now, I'm pretty confident that you have learned how to solve this polynomial before, okay? Probably in your junior high school, right? Now, lambda actually have two possible values. This is one of them, this is the other, okay? The solution of these differential equations can be divided into three cases, depending on the difference between a squared and 4b is larger than 0 or equal than 0 or smaller than 0. Because if it is larger than 0, what we have is we will have two real roots, lambda 1, lambda 2. Both of them are real numbers. Otherwise, for example, if a squared is actually equal to 4b, then what we have is a pair of roots with identical values, or a real double root, okay? Now, if the third case, in the third case, a squared minus 4b is smaller than 0, and then what we have inside the square root is a minus number. So what we will get is a pair of complex conjugate roots, all right? Now, these are the three cases, three possible cases, okay, for the homogeneous solution for this so-called second order linear differential equations with constant coefficients. Now, for our problem, our linear differential equation come from here, and its characteristic equation is this, which corresponds directly to this characteristic equation. So, if lambda is the eigenvalue of this ODE, then S as the root of this characteristic equation represent the pole of the spring mass damper system. Okay, now it can be shown that by solving this polynomial for its roots, this is what we will get. Okay, similarly to what we get here, we apparently have a pair of roots, and depending on lambda squared, lambda actually is larger, equal, or smaller than 1. Similarly, the Zell input response, the pattern of the Zell input response of the spring mass damper system can be divided into three different scenarios, okay? One is eta equal to 1. The other is eta larger than 1. And the third is the value of eta is between 0 and 1, okay? For the case of lambda equal to 1, we call it critically damped case. For this case, the poles are actually a pair of distinct value real numbers, okay? Now, this is referred to overdamped case. The reason why it is overdamped, because among these three cases, this case has the largest value of damping ratio, okay? For the underdamped case, eta is between 0 and 1, okay? Now, let's go to this figure. What is this all about? This apparently is X complex plane, okay? Now, X actually is a complex number. Its real part is sigma. Okay, its imaginary part is omega, right? Okay, so the location of the poles of these spring mass damper systems can be plotted as this contour, all right? It's in the beginning, let's say eta equal to 0. What we have is a pair of complex conjugate roots, but this time the real part is 0, okay? So initially, when eta is equal to 0, our poles are located here and here, all right? Now, let's imagine that the value of eta is being increased incrementally, okay? Step by step. So initially it's 0. Now it becomes larger and larger and larger, okay? Now, this pole will move downward, and this pole will move upward simultaneously. Why? Because they are a pair of complex conjugate roots. They always have the same real part, and they always have the same imaginary part in terms of magnitude. But of course, okay, they have opposite signs, right? Now, once eta becomes, the value of eta reaches 1, okay, the location of the poles will, one of them will go go to leftward. The other will go to rightward, okay? Let me put it another way. One of the pole will move in the negative direction. The other will go in the positive direction, all right? So this essentially is the trajectory of the poles of the spring mass damper system, okay? As you can see, the location of the poles depends on eta, okay? Depends on eta. Whether you have a pair of real poles with distinct values or a pair of poles with identical values, or you have a pair of poles which are complex conjugates. It all depends only on one parameter, which is eta. Okay, so eta depends basically the basic response pattern of the zero input response. Okay, but remember, we just say that there are 2 key parameters for spring mass damper system. One is eta, and we now see what eta do to the poles. And what about omega n? And omega n, this is, you can see this as a circle, okay? Where the center of the circle is located as the origin, okay? And the radius of the circle is actually omega n. How do you do that? It is actually very easy, okay? Look at this triangle, okay? You take the square root and add to the square root of this term, and then you take a square root again. What you will see is omega n. So the distance, once the poles are located at this circle, the distance between the pole and the origin is omega n, all right? So omega n pretty much determines how far away the poles are from the pole, okay? And okay, so geometrically, you know what eta and omega n do to the locations of the poles. Now, let's go one step further, okay? Now, when I represent our poles in this way, essentially, we are using a Cartesian coordinate system to represent the location of the poles, right? This is the real part, this is the imaginary part. This corresponds to the horizontal axis, and this, of course, related to the vertical axis. Now, we can use different coordinate systems. Now, let's look at this problem, not from the view of Cartesian coordinate system, but from the view of polar coordinate system. Why do we want to do that? Because it will simplify our problem. Okay, for an engineer, the only reason we want to use a different tool, different methods, okay, different approach, is because by doing that, things can become more efficient. I can solve the problem more effectively because we are engineers. We think practical values matters, okay? Of course, we are not scientists, okay? Scientists can do things purely out of curiosity, okay? Whether it is useful or not is not their concern, okay? Their major motivation is to discover new things, to understand the working principle of things, to understand how nature works, okay? How animal responds to different threats or environmental changes. Whether or not those findings are useful for mankind, or it sometimes really unknown, okay? But our engineers, whenever we do anything new, there is only one motivation behind it. The new stuff is useful, okay? So now let's switch to polar coordinate representation. Now, in this case, let's assume that we have a pair of poles located here, okay? How do we represent their location? The first is, of course, omega n, which it represents the distance between the pole and the origin. The other is this angle, which is denoted as theta. And it can be shown from here that cosine theta is actually equal to eta. So once you know theta, once you know omega n, pretty much you understand the two most important parameters of the second order system. All right. So omega n sets the radius of the pole location. Okay. And as I will tell you in the later part of this lecture, omega n pretty much determine the speed of response of the system. And theta sets the angle of the pole, which is directly tied to damping ratio because eta is equal to cosine theta. For second order linear time invariant system, the poles can be represented either in Cartesian coordinates, which is this representation, or in polar coordinates, okay? And we prefer polar coordinates because these two coordinates directly related to the two distinct key parameters of the second order system. All right, now let's go back to our original problem, which is set up to determine the zero input response of the system. Now, how do we do that? In the course of engineering mathematics. Now, we learned that before. As we just discussed, is zero input response or the homogeneous solution of the second order differential equation can be divided into three cases depending on the values of the roots. In the first case, we have two distinct real roots. Therefore, the solution is this, right? Because we assume y equal to e to the lambda x in the first place. That is the beginning of, that is the starting point of our solution process. Okay, so of course, our solution is the linear combination of these two modes, right? Okay, now if I have a pair of real double roots, then the course, my engineering mathematical course, taught me that the zero input response or the homogeneous solution of this ordinary differential equation is this. All right. Now, for the third case, okay, which I have a pair of complex conjugate eigenvalues, and this is what I will get for the zero input response, or this is what we will have for the homogeneous solution for this differential equation. Now, so this table summarizes the results for the solution and the solution process of the homogeneous differential equation. All right. Same thing. We can generalize, or we can directly. I'm sorry. Let me take a very short break. All right. Learning is sometimes very hard, okay? But it pays off, okay? Now, for you to have something positive to look for, I want to remind you that we will have a long weekend, okay? Because after tomorrow, Friday is national holiday, and then Saturday, and then Sunday, 3 days, okay, consecutively, you can have a hopefully a wonderful time, okay, and take a deep break, take a break, okay. Now, okay, we can convert this result directly to our spring mass damper systems because mathematically they are the same thing. They are all second order differential equations, okay. Now what we can do is we remember that this is the zero input response of our zero input response of our spring mass damper system. We can take inverse Laplace transform of this representation, or we can approach the problem in an identical way as what we have done here. All right. Now let me summarize the results here. Similarly, what we have here in this table, okay, the zero input response for the spring mass damper system can be divided into 3 different categories: underdamped, critically damped, and overdamped. All right, okay. Now let's focus on overdamped and underdamped responses, okay? When you have an overdamped system, the mathematical representation of the zero input response is, overdamped is here, okay? Now, to the system, because spring mass damper system are always asymptotically stable. Therefore, R1 and R2 are both negative. As a result, okay, for the overdamped case, the zero input response of the spring mass damper system will have a shape similar to this blue curve. It will decrease monotonically with time, all right? And the decreasing rate, we call it, it decreases in the exponential rate, okay? Or we say it decreases exponentially with time. But for the underdamped case, which correlated to the case of the value of eta turns between 0 and 1. The zero input response now look like this, all right? As you can see, one of the fundamental difference between this and this is that we have sinusoidal terms for the underdamped case, which means the zero input response for underdamped spring mass damper system will have oscillations. All right? Acceleration. Now, the dotted lines here represent the envelope of the response. Why do we have this envelope? Because e to eta omega nt appear outside this bracket, okay? And inside this bracket, we see sinusoidal functions, all right? But we all know that the value of sinusoidal functions are always between 1 and -1. So pretty much this determines the envelope of the zero input response for the underdamped spring mass damper systems. Now, the question here is how the poles relate to the system behavior. Let's focus on underdamped case, all right? Okay. The reason why we want to focus on underdamped case, because overdamped case, typically for our control applications, are simply too slow, okay? Now, if we are dealing with underdamped spring mass damper systems, then poles are always complex conjugates, and they are always located in the left half plane, which means that they are always, such a system is always asymptotically stable. And these are the poles, which is a pair of complex conjugate numbers. Here, let me introduce a new term, which is called damped natural frequency. Of course, omega n represent natural frequency, and sometimes omega n is referred to undamped natural frequency, okay? Here, omega d is called the damped natural frequency. Where does the idea natural frequency come from in this particular case? The reason why we introduce damped natural frequency is we discovered that for the undamped spring mass damper system, or more generally for the undamped spring linear second order time invariant system, its oscillation frequency is actually omega d, not omega n, okay? So that is why omega d, or what we call it damped natural frequency, is important, because it pretty much characterizes the speed of oscillation, the frequency of the oscillation of the zero input response, all right? Now, as you can see here, since eta is between, the value of eta is between 0 and 1, the damped natural frequency is always smaller than the natural frequency, all right? It's always smaller. Why is that the case? And it is easy to see, because what we have here is a spring mass damper system. Without a damper, it is easier for this mass to move around in high speed. But once you introduce damper into the system, you introduce additional resistance force. And that resistance force is apparently, by definition, proportional to the moving speed. of the mass. All right. So after introducing damper, the acceleration speed of the mass, of course, will reduce. Okay. It can be proven mathematically, but physically, it is always to see why is this the case, right? Okay. Let's go one step further. Okay. Now, we want to understand more about the location, the impacts of the location of the pulse. And now remember that the pulse is actually a complex number, right? This is the real part, and this is the imaginary part, all right? So the real part, again, let's look into this case, underdamped case. And remember that what we are studying right now is the zero input response. Here, we don't have any input. So what we are studying is the basic behavior of the system itself. We are studying the nature of the system, all right? So here, explain this blue curve represent the envelope, okay? Exponential decay generated by the real part of the complex pole pairs. That means the envelope, which is this term, is actually because, let me write it here. X12 is equal to eta omega m plus minus j omega d. And this blue curve, I'm sorry, is actually E minus eta omega and t. Right? Right? Okay, so that's is where the envelope come from. Okay, so the envelope is actually determined by the real part of the pulse. That is the reason why we have such a statement, which tells us that exponential decay generated by the real part of the complex pole pairs. And let's look into the second statement. Sinusoidal oscillation generated by the imaginary part of the complex case. The frequency of this oscillation pattern is omega d, right? Right? And omega d is actually the imaginary part of the pulse. Okay, so for now, once you know where the pole are located, probably one of the first things you can do is to determine how far away is this pole from the imaginary axis, and how far away is this pole from the real axis, because these two terms, they all have very direct physical meanings when it comes to the zero input response. All right? All right? So the impacts of the location of the poles on the zero input response can be explained or can be illustrated by these two very nice statements. All right, let's go one step further. What we have just did is we discuss how do we generate zero input response of the system, and essentially we study the zero input response system and discovered that the patterns of the zero input response can be divided into three cases. And the principle of division has everything to do with the nature of the pulse, okay, which I have a pair of real poles, or I have a repeated poles, or I have a pair of complex conjugate poles. Now, the focus here now switch to impulse response. Now, again, we want to focus on these two key parameters, natural frequency and damping ratios. Okay, now here, let's go back one step further. Go back one step. Let's study the zero-state response, which is this. Okay, zero-state response in the X domain is actually the product of the transfer function and the Laplace transform of the input. Okay, as I have said it several times, this is a beautiful result. This is a beautiful result because it uses one simple mathematical operations to connect to connect the relationship between input and output. Okay, and that mathematical operation is multiplication, which you learned when you was in elementary school. Now, if you take inverse Laplace transform of this, what you will get is convolution integral. We talked about it before. Okay, well, h of tau is the inverse Laplace transform of the transfer function, and h of t is therefore called the impulse response. Why is it called the impulse response? Because if you take the impulse function, take the Laplace form of the impulse function, what you will get is 1, all right? And if this is 1, then yzx is equal to h of x, okay? But remember, this is true only when the input is an delta function or impulse function, all right? So if I take the inverse Laplace transform of the transfer function, I'll get the impulse response. Now, the impulse response in the time domain, again, similar to the zero input response, can be divided into 3 cases, okay? And the rule of divergence, again, it depends on the value of eta, okay? Which is, if eta is smaller than 1, then we have underdamped system. If eta is equal to 1, we have critically damped system. If eta is larger than 1, we have overdamped system. And these are the mathematical representation of these 3 types of impulse response, okay? I will not go through the mathematical details to tell you how do we get these representations or how do we get these mathematical results, okay? You can use the Laplace transform, okay, to find these results. No big deal, all right? Now, let's go one step further, okay? The first thing we check out today is their input response. The second thing we study is impulse response. Let's move one step further. Unit step response, okay? Which means the input now to the system is a unit step function, which has a value of 1 once t is larger or equal to 0. Now, again, similar to what we have for the zero input response. The unit step response of a spring mass damper system, again, can be divided into 3 different scenarios or 3 different categories: overdamped, critically damped, and underdamped, all right? Now, before I go one step further to derive the unit step response, I want to revise our equation of motion, okay, slightly. Now, originally for the spring mass damper system, this is what we have, okay? I'm sorry for the inconsistency of the notation, okay? But M again represent the mass, B represent the damping coefficients, which is denoted as C previously. Now, K again is the spring constant, and R represent the force applied to the mass, all right? Now, if with such a representation, the steady state output of system will be this. Where does this result come from? Remember, here I assume steady state, which means when time goes to infinity, y will become a particular constant, okay? Y cannot be changed, will not change anymore. It will be a fixed constant. If y is a constant, then y down is 0. Y double down, of course, is also 0. So in steady state, this go away. This go away. What we left is ky equal to r. Okay, this is what we have. So this is only true for steady state. This is the reason why we have a subscript here, SS, which apparently denote steady state. Okay, now so to make yx equal to 1, okay, we must set r of t equal to k. Okay, so this means with such a representation, what we have is we need RT, the input, to be K in order for the system to have a steady state value of 1. Okay, that's not what we want. What we want in the context of control is that the input is essentially a target output. Okay, the input is essentially a command. Okay, so put it another way, it is essentially the desired output. Okay, here the input is K and the output is 1. Apparently, they are not compatible. Okay, so how do we deal with this? How do we deal with this difficulty? Well, actually, it is not difficult at all. However, by modifying the equation, let's introducing a K here. We here originally on the right-hand side of the equality of the equation, what we have is RT. Now, let's times RT by K. All right. If this is the case during steady state, again, this go away, then YSS, which is the steady state output of the system, will be exactly the same as the input. All right. So in the remaining part of this course, next time when we deal with second order systems, next time when we deal with a spring mass damper or spring mass damper system, this will be the equation of motion of our system. All right. Now, if this is the Gaussian differential equation of the system, or the so-called equation of motion of our spring mass damper system, then it can be shown that the transfer function will look like this. Okay, again, by using natural frequency and damping ratio, transfer function now can be rewritten as this. Okay, now the denominator is exactly the same as before because we didn't make any changes to the differential equation itself, at least not on the left-hand side of this equality. Okay, the dynamics of the differential equation stay the same, which means the poles remains the same. The only difference is that here in the numerator, it used to be 1. Now, after introducing k on the right-hand side of this equation of motion, the denominator is now omega n squared. All right? So, okay. Now, after introduce, okay, let's take a 10 minutes break. OK， 如果要看考卷的话，可以来跟学长拿。If you want to see your examining sheet for the first midterm.